So last math club of the semester of the calendar year will be today, March 102. We've got math science major who actually did an internship doing stuff with sports analytics. So that ought to be a lot of fun and show you how maybe you can get an internship and you'll learn how math connects to that. Don't forget, math can take place tomorrow in this building. From 10 a.m. to 5 p.m. It's a good time to show up. Going to get fine-tuned files. Got them coming up. Also, I can hopefully guarantee partial freedom on one day. And I hope I'm not getting some time to do that. We've got a lot of stuff going on this week. So we'll say 7 a.m., 6 p.m. Monday. I'll be there. I'll be in my office all day. Or point. I've got 2 PhD exams that I have to sit in on and all that, and it's kind of crazy. But I might be able to squeeze this indeed. How about this should not keep you from coming to the math end, but I do try to have a great part about this. Review session, how about Tuesday night? Let's say, actually, let's say, does anybody have, why don't we say 4 o'clock? Does anybody have any exams that are like later than that on Tuesday? The only reason I do that is so I don't have to deal with their crazy block building crap. So let's say Tuesday at 4 p.m. That work for folks? And I'll get that set up. Okay, any questions? Oh, also remember to do the evaluations, because if we hit 90%, then I will give everybody an extra good score. And of course, I've got to know that early, so get that done before the final. Also, don't forget, if you haven't done your last assessment thing, then you need to get that done. I guess you could all be Monday, but besides that, you've got the day. Well, okay, questions? All right, so I've got a couple of examples. Yes. Yes. Yeah, it will. The exam will be cumulative, and it will be sort of like your other exam. In fact, if you look at the old exams, I'll probably kind of good theme. Once again, there will be questions on definitions, short answers, and the other stuff. It will be longer, as you might guess. I do not design it to fill the 2.5 hour period. In fact, in a perfect world, what I expect is you will be able to finish it, carefully check it over and turn it in and say kiss off to me and fly off for Christmas in 2 hours. I hope. Okay. Other questions? All right. So I've got a couple of examples. So let's. So let's just go about this. Actually, I think last time I did a 2x3, which in a certain sense is easier. When you have like more rows than columns, there's some filling in that you have to do. It's a little extra work, and we'll see that in this example here. So I want to take this matrix here, find the single value composition. The first thing I do is I need to figure out ATA. So so I need to multiply these matrices out to make a square. This should be a symmetric matrix. That's a gut check. When you do the step, it better be symmetric. And also, in the next step after this, I'm going to have to find the eigenvalues and the eigenvector. The eigen, what has to be true of the eigenvalues? That is correct. Well, or at least zero, right? So let's see what happens. This row comes 5. This comes, this is 2. This comes, this is 2 again. That's a good sign. And this time, this is 2. So I get this matrix. Now, what I need to do now, of course, is I need to find the eigenvalues. Because I need to orthogonally diagonalize. So I need to orthogonally diagonalize this matrix as a piece of puzzle, and this will actually give me a piece of what I need to do. So I'm going to sort of put this data over here as we did it. So let's go about trying to find the eigenvalues and eigenvectors. So look for the determinant of 5 minus x minus x. This gives me x squared minus 7x 6. And this is x minus 6. X minus. Okay, so I've got eigenvalues. Let me report this. Right, okay. So what are my singular values? What's the relationship between the eigenvalues of this and the singular values for the matrix? The original matrix. Correct. So singular values for the original matrix A are square root of 6 and 1. And we arrange these and decrease them. Okay, so fine. Okay, I need eigenvectors because I'm going to need the eigenvectors to orthogonally diagonalize this. Notice that so far everything's good because I've got all non-negative eigenvalues. 6, 1. So let's look at lambda equals 6. This gives me the matrix -1, 2, 2, minus 4. Lucky me, of course, and this is again a good gut check. This means I'm on track because the second row is multiple first. So I get an eigenvector. I guess I can go. I'm doing this rather quickly, but really notice that when I take this matrix times this vector, get 2 minus 1 get 0. Right? So I know that's beautiful. So the corresponding eigenvectors in order are 2, 1. We got to find the other one. For lambda equals 1, I get 4, 2, 2, 1. Right. And this is if you put your eyeballs on this and tell me an eigenvector for that one.
Oh, sorry, -1 to.
Agreed. So, what is the matrix that I need to orthogonally diagonalize this? The diagonal matrix should be that. Correct. And let's see, this should be B, so it should be the eigenvectors in order. Is that right?
Oh, right.
What's in it?
Transfer.
No, that's not the mistake I made. Or I'm not complete. This isn't quite right. Because I put the eigenvectors in there in order, but right, you got to normalize. That's right. And so notice the length of each of these is radical 5. So really I need to do this. And the inverse should be, and Griff, this is what you were thinking. I think the inverse of this thing should be the transpose. So the piece over here should be 2 radical 5, 1 of the radical 5. And actually, it's fairly easy to check these two things are and actually, if you multiply this all out, if I've done this right, multiply this comes this, and you take that, multiply by that. But I need this because this is going to be important. Yes, sir. It is not the finished thing. What I have found so far is I have found the diagonalization, the orthogonal diagonalization of not A, but this square thing, right? But the reason I bothered to do this is this piece, the VT, is going to come up in the orthogonal in the singular value composition, and this piece, the V, is needed to figure out what the U is, right? So, in fact, let me kind of capture this. Here's what I know so far. A is equal to U sigma VT. And I already have some of my answers here. There's your VT. What's your sigma? Now remember, sigma should be the same size as the original matrix A. This one right. So it's got to be 3 rows by 2 columns. How many non-zero singular values do I get? How many non-zero singular values did I get from this computation? I have 2 of them, radical 6 and 1, correct? There's 2 non-zero singular values, so that makes a 2 by 2 block. I've got them. That's not a 3 by 2 matrix. So fill it up with 0. Finish it off. So as far as singular value decomposition goes, I'm 2/3 of the way. I got my sigma, I got my VT. All I've got to get now is U. Now remember, U, I, this is one of the columns. U is supposed to be 1 over sigma I and DI. Now, does anybody see what difficulty we're going to run into that we didn't run into when we had a 2 row by 3 column matrix? Let me ask you this. What should the size of the matrix U be? What does it need to be? See, VT is 2 by 2. this is 3 by 2. What should you think? 3 by 3, right? Somebody tell me what's going to be the problem here when I try to build my U? Yes. Right, I'm going to run out of gas, right? I need 3 columns for you, right? But I've only got 2 columns for the V. So if I look at that formula up here, this only gives me enough information to get 2 columns, right? So U1, and let's just do it. U1 is 1 over sigma 1 A D. Okay, well, let's see what that is. Sigma 1 is radical 6. A is my original matrix here. And B1 is the first column of B, not a B transpose, B. So it's 2 over radical 5. And so what I get here is I get 4 over radical 5 plus 1 is 5 over radical 5 by 6. So I get 5 over radical 30. And let's see, the second, this is pretty longer. The second one is going to be minus 1 over radical 30. And the last entry is going to be 2 over radical 30. 2. Here, sigma 2 is convenient with 1. The second column of this V is minus 1 over radical 5 and 2 over radical 5. So this turns out to be, again, 3 high column, minus 2 over minus 2 over radical 5 plus 2 over radical 5, 0, minus 2 over radical 5, and minus 1. But of course, if I want a 3 by 3 matrix, I need a third column that looks like this, right? And I've run out of columns of V to use in that formula. So what do you do? I mean, how do we resolve this problem? Well, the only thing that really matters now is for you to be an orthonormal matrix. The third column matters less. So all I need to do is to, I'm going to actually call this B1. This is going to make my life easier. B2. Notice this is related to U1 because all I've done is nobody wants to do computation for radical 30, right? So I just multiply this by radical 30 to make it easier vector. And nobody wants to do computation for radical 5, so I'll multiply this to make this an easier vector. Now, what I need is I need a third column that is orthogonal to both. By the way, notice that these 2 columns are orthogonal as they should be. Because the dot product here is 2 minus 2 is 6. So I need a third column that is orthogonal to both of these. And anything will do, of course, 3 by 3, I've already got 2 of them. Basically, only one. Well, there's only one vector up to scaling that I can get this last one. So how do I get this third orthogonal column? What's that? Gram-Schmidt. Yeah, that's right. So that's again, this is kind of an application of Gram-Schmidt. Now, what I need is I need a third vector as a seed, right? Because remember, what Gram-Schmidt does is it takes a given basis and it does its magic and turns that basis into something normal. So the problem is, I've got two orthogonal vectors, and I need to expand this to an orthonormal. Yeah, these are two orthogonal vectors. I need to expand this to an orthonormal basis of R3. But I've only got two things. Can anybody, what's the third vector that I might use to see? All I need is something that's linearly independent with these two. These two are orthogonal, so they're linearly independent. I just need a third vector that's linearly independent. So you can kind of make this up. Looks like B3 equals now. Make it as easy as possible. Anybody see the easiest possible vector you can think of that's going to be linearly independent from those other two? Well, the problem is 0 by itself is not linearly independent. Yes. I think you are correct, but I'd have to verify. Go with your idea, make it a little easier. How about that? Right. This will be linearly independent of these two. And the reason is clearly none of these are multiples of each other. And there's no way that a sum of a linear combination of this and this is this. Because if something times this, something times this, and you've got to multiply that by 5, and you're done. And now you've got to multiply this to match the third coordinate. You've got to multiply this by -2, and it doesn't work here. So this is a third linear. You've got to find that. But now, use Gram-Schmidt to find. So here's what we're going to do. We're going to let U3 equal B3 minus B3 dotted B2 over B2 dotted B2 minus B3 dotted B1 B1 dot B1. Let's see what comes out of this. Now, this is yet another reason why this choice was good. What happens when you've got B3 and B2? You get 0, right? That's very convenient, right? Because this is 0. So it's going to be 0 over, I don't care, 5 pound B2. Now you got about B3, B1, and I get 5. B1 dotted with itself is 30 times 5 minus. So I get 1, 0, 0. And this is going to be minus 5, 6, plus 1/6, minus 1/3. So this gives me the vector 1/6, like 1/6 minus 1/3, and I'll scale this up. So again, I just multiply that vector by 6 so that I get something. Yes. So let me give you the U that works. All you got to do is normalize B1, B2, and this new vector here. So I get 5 over radical 30 minus 1 over radical 30. 2 over radical 30. Second column, that should be 0, minus 2 over radical 5, minus 1 over radical 5. And last column, I'm going to divide by radical 6. This vector. That's correct. And you can check this, and you can, so if you're still a little uncomfortable with it, here's your U right here. Take that U, and then the sigma and this VT, and you multiply them all together, you will get the original A, 201, 1 minus. Okay. Any questions? Yes.
So you'll still get the same result. Like
in this case, yes, because what happens is you're an R3, right? And you've already got 2 linear vectors. Imagine a plane sitting in all space. There's only one way to get back to perpendicular to that plane, right? And of course, there can be different vectors, but every vector is a multiple of this, right? Negative multiple. And so, yeah, I think you suggested first 1, 1, 1, which I believe is also linearly independent. If you had done this, we would have ended up with the same vector or a multiple. Okay, any questions? Okay, so I promised to talk about this. I've got other examples too. I'm going to get this here. Let me see how well we can do this. Oh, by the way, this is the worst quiz for you guys, had the lowest average. The quiz after that had the highest average. So, and I've got pretty much, the next quiz actually was due Monday at noon because I was a little late on this. I think it will be very similar. It'll do some computations like the previous quiz. So I hope you guys do well. Okay, so let's take a look at this. So the first thing we're doing is we're considering vector space D forward. Let me remind us all what this is. This is all polynomial. 3, 4 smaller, including 0 polynomial. Every conceivable 4-3 polynomial. In the first problem, I define this inner product just to be A0, B0. So multiply the first term together. I multiply the second term together. I multiply the third term together. I multiply the fourth term together. And then I multiply the fifth term. And then I add them all up. Does this remind you of anything? In fact, it's exactly, I mean, this isn't really the dot product because I'm writing things in a different form, but it's it's very analogous to the dot product, right? Because imagine if instead of pluses here, I had commas, and this is Right, if I just had commas here and this, and then you think of this as a vector with 5 coordinates, this is just the dot product, right? So it says, let, funny looking E span of 1 x squared x. Find the orthonormal component. Any ideas on how to do this? What if I had the regular dot product? Right, so let's just kind of take this sort of different. I'm just gonna think, if I had span, see, we got say 1 x squared. This is the analog, right? This is like 1, and this is like x squared, and this is like x squared. Right? So, can anybody give me 2 vectors that are orthogonal to all 3 of these? Correct. I'm going to write it this way first, but you did it better. Everybody agreed that those 2 vectors are orthogonal to both of them. And you can just do the computation and check. So notice that E per x and x cubed are again. And now that you know that, you're done. I know.
Is there already working?
Okay, when you say orthonormal for who? But when you say something's orthonormal, you're comparing.
So it's already in comparison.
Right, well, in fact, we're going to get a bonus later because in fact, not only are these 2 vectors, this is orthonormal to every one of these. Well, this is orthogonal to every one of these, and this is orthogonal to every one of these, and it turns out they're also orthogonal as well. And they're also orthogonal to each other. What is the dimension of P4? It is 5. Everybody agree with that? What is the dimension of this? It's 3, right? You got 3 bases. These 2 are linearly independent elements in the curve, right? So the dimension of this is 2. The dimension of this is 3. You've got everything done. Right? Okay. Right? Because I know that both of these are perpendicular. This is a 2-dimensional subspace. This is a 3-dimensional subspace. There's no room for anything else. And number B, use the Gram-Schmidt process or any technique you like to find an orthonormal basis for E. So, anybody want to know what the orthonormal basis of E is? Actually, 1 x squared x squared. It's already basis. All those elements are orthogonal to each other using my so-called dot product, right? Because 1 is just, this is 1 and the rest are zeros. And for example, x squared is B2 is 1 and the rest are zeros. Notice this formula that gives you 0. So these 3 are all orthogonal to each other. And the length of all of them is 1. Because when you take the inner product of 1 with itself, you just get 1. When you take the inner product of x squared with itself, you just get 1. And when you take the inner product of x4 with itself, so they're already orthogonal to each other. They're already at length 1. You're done. That's it. Everybody okay with that? So, Now we change it a little bit. Inner product 2, and I don't bother to write out coordinates this time. What did I do? Mine's moving. And actually, my choice of the interval is helps you with the problem. Find the orthogonal complement. The first thing I claim is X is in the orthogonal complement. And I'll do it quickly. If G of X is in E, span of 1 x squared x 4, what does G of X look like? It looks like a polynomial with all even power terms, right? Do I agree with that? So if you look at the inner product of X and A plus BX squared plus CX4, I claim this is always equal. It doesn't matter what it is. And here's the reason. This is the interval from -1 to 1 of AX plus BX2 plus CX5. And that's always equal. Why? I mean, I'd rather not do computations. Yeah.
Because
Whenever you integrate an odd function on a symmetric interval, symmetric by 0, you always get 0. And you can go through and do the computation if you like. I promise you will get 0 because this is not a function. Everybody okay with me? And something similar is going to come up for the other piece. I also claim the same reason that also x cubed is in E. For the same reason, because if you look at the inner product, it's x cubed and A plus bx squared plus cx4. This is the interval -1 to 1 of ax cubed plus bx5 plus cx7. And that's 0 too, because it's an odd function, symmetric. So now I've got the same argument that I had before. So x and x cubed are in E per and are linearly independent. So span of x and x cubed is exactly E per, because it says dimension 2 and E itself has dimension 3, so that makes. Okay, and finally, use the Gram-Schmidt process or any technique you like to find an orthonormal, an orthogonal basis for E. So I'm going to turn this off now. Into that. This one gets a little bit ugly, and you will probably quickly see why I asked you for an orthogonal basis and didn't care too much about orthonormal. I'll say something about that. So, let's start with our basis in the first place. And let's use Gram-Schmidt to refine this and make an orthonormal basis. I'm sorry, an orthogonal basis. I'm going to call this P1, P2, P3. Those are my 3 basis elements. So my new basis is going to be B1, B1, 1. Do my usual kind of start off there. I want B2 to equal B2 minus B2 inner product B1, B1, B1. Okay, so we'll see what kind of mess this is. B1 is B2 is x squared. Inner product of B2 and B1, that's going to be integral of minus 1 to 1 of x squared dx. And the inner product of B1 itself is that times the vector B1, which is, maybe this would be too bad. This integral right here is 1/3 x cubed evaluated minus 1, so that's going to be actually 2/3. And this integral is actually x evaluated minus 1, which is 2. So I get x squared minus. There's your B. And finally, B3, this should be B3 minus inner product B3, B1, 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 on B1, and B3, B2, B2, B2. Yes. This right here, interval 1 dx. So, 2.
Oh, wait, no.
One's an even function. Right, so doubles. So this, so let me take a little side over here and do some computation. What am I going to need to do this computation here? We'll take a little aside here. B3, B1. So that's going to be 1 times B3, so that's x4. Next, this comes out to 2/5. This is 1/5 x5 evaluated. Basically, it doubles the 0 1. B1 is 2. We've already done this. Let's see, what else am I going to need? I'm going to need B3, B2. This is the interval from minus 1 to 1. X to the, like, x to the 4 times this mess here. So it's going to be x to the 6 minus 1/3 x4. Yes. So it's going to be x4 plus 1/4 dx. So this is going to be x to the 7 over 7 minus x 115 x to the 5. And this is going to turn out to be 8 over 16 over 1. 16 of the and B2 rather obnoxious. It is x minus 1/3 squared. Oh, I'm sorry, it's x squared minus 1/3 squared. And so this is integral from minus 1 to 1 of x to the 4 minus 2/3 x squared of 1/9 dx. So this is 1/5 x to the 5 minus 2/9 x cubed plus 1/9 x. And so let's see. So that's going to be this is what, 8 bits, I guess. Yeah, it was 8 bits. So it looks like I've got everything you need. So this is going to be B3, which is x to the 4, minus this number over this number. So that's going to be B3, B1, which is 2/5 over B1, B1, which is 2. So I get 1/5 of B1, which is 1. So it's just 1/5. This number over this number, that's going to be 16 over 105 divided by 8/45. Times B2, which is x squared minus 1/5. And so whatever the difference comes out to be, x to the 4 minus 1/5. This turns out to be 90 over 105, which is the same thing as 30 over 35, which is 6 over 7. So I get x4 minus 6/7 x squared. And let's see, this would be plus 16 first. So this is 30, 9 of 1, this is 3/30. And there's the last fractional basis. Okay, quickly, somebody answer this quick quiz question. Why did I ask for an orthogonal basis and not an orthonormal one? That is right. Very good answer. My teacher is a lazy man, and he does not want to integrate. Because really, to figure out how long this thing is, I've got to take the inner product of itself, right? So I'm going to have to multiply this out. It's going to be an 8th degree polynomial that I'm going to have to integrate. It's certainly doable, but nobody wants to do it, right? Any questions on that? All right. I guess that's about it. We'll take advantage of your resources. We've got the math in tomorrow. We're going to have a review session Tuesday. I will be in the office all day Monday. And I will tell you, I've enjoyed having you in this class. Once my student, always my student. So if I can be of help in the future, be sure to let us know. Hit some button on the file and have a good break.